Hey there! In this video you will discover how to make your AI agent performing really big tasks requiring hundreds of actions in just a couple of minutes and super cheap. Let's take an example. Imagine you want to find a co-working space that is close enough to you, but you don't want to go over each of them and click directions and see how much it would take for you to walk or to drive, but instead you want something to do this automatically for you for all the locations around you. But at the same time, you don't want to use Perplexity because first of all, you're not sure if it will find all the locations. Secondly, it will just summarize the information on the internet. But you want to be precise. You want to explore all the locations that are available on Google Maps. And you don't want to miss anything. And it all has to be within a certain radius from you. In order to do this, we will use LangGraph. In this video, I expect you to already know what is that. If not, you need to check out yourself. We will also connect it to two different MCP servers. You also need to understand what is that. One is for Google Maps to pull the locations, and one more for Notion to store all our data. And in LangGraph, we will use the ReAct agent pattern, reflect and act. You also need to understand what is that in order to be able to reach up the context of this video. The rest I will explain. Let's try it out. It will create a database inside this page with all the coworkings around the location I will just show in within 5 kilometers, and this table will contain the name, address, website, and also the walking distance from that address. And we will be using the ReAct approach I've been talking about. So it starts. Let's check out the traces. As you can see, it starts calling the tools one by one. So first it will check all the places around that latitude and longitude. Then it will create a database on Notion, and then it will start adding all the co-working spaces one by one, and also look for directions to each of them. Okay, now it's done. Let's see. So it only added 3 co-working spaces, but on the maps you see there are more. Also, if we go to the traces, to the place search tool call, we can actually just search for rating, and we can see that there are at least 18 results. So something is wrong. And this is the first problem we have with this approach, because the model is just non-deterministic, so it may give up at any point because it will just decide that it's enough. And in order to fix that, we can, for example, retry it again and say that we need to have all the 18 co-working spaces that we saw in the API response, and retry again. And even after specifying that I need the 18 co-working spaces, it still just added 3 of them. Again, we can prompt the model, we can put lots of exclamation marks and say that we need the 18 co-working spaces, but basically this is the first limitation we have with the models, because it can just give up too fast and consider the task to be successful, or that it just needs to ask for a confirmation with the rest. And after 4 iterations, it managed to add all of them. Again, with the right prompting, it will do this from the beginning, but the point is different. The point is the cost. If we sum it up for these 4 runs together, we can see that it costed us almost $4 to just fill in this small list. Why it happened? It happened because of the long chat history it has to go through in order to accomplish this. And the more tools it was calling, the longer the history was becoming. So it was just spending more tokens every time in order to accomplish it, as you can see here. So the history got pretty huge. A workaround could have been using parallel tool calls that were introduced by OpenAI so that you can call different tools in parallel, and this way it would also cost you much less to run it. But the problem is that the API you use might just be not supporting that amount of calls to be done in parallel because of the rate limiting. That's why such things have to be done in a much of a smarter way. And this is basically the topic we'll discover today. What if instead of calling the tools one by one, or even in parallel, our agent would just write the code, just like an engineer would do? This approach is named CodeAct. There is also a paper that introduced it. Feel free to just pause and read it in. I will also leave this link in the description. This way, instead of calling each of these tools one by one, you can just have a single loop, a single piece of code that would execute, finding all these places and saving them. Let's try it out. So we do the same thing. Now we don't need to specify the amount of co-working spaces because it will be more deterministic. We chose CodeAct as an approach, and we go check our traces. As you see now, it doesn't call tools, but instead it generates a code. For example, this one extracts the page ID from the Notion URL. That one geocodes the location address to get the coordinates. And now we can see how fast it is. After that, it searches for places, extracts the details of just one of them so that it can gather the information about how the structure is looking like. This is also nice because it outputs everything in the context window, and the less data it outputs, the cheaper it will be for you at the end to pay for this. And just one single record is enough for it to construct the algorithm of how it will interact with this data for the entire list of places. Then it gets the distance information for each of the places, again, just as a single call. And the final thing, it creates the database, and then it populates the entries of this database. And everything happens in a single code execution. And now let's see how much did we pay for that. If you come back to the root, we can see that it costed us just 50 cents. It is 9 times cheaper than the thing we did before, which is incredible. And the nicest thing is that if, for example, we will process not just 20 items, but for example, 200, the price would be pretty much the same because it will just output a single item again in the step when it was exploring the place details. Of course, sometimes it may hallucinate, but these things can be fixed with the prompt, but at the end, you just save 9x by writing the code. And the nice thing is that it is reliable. Code running can also be speeded up because here we use a sandbox. We use Pyodide for that, an environment where you can execute the Python code right inside the browser. It uses WebAssembly, and this is also the standard practice for running Python code in a safe environment because we don't trust LLMs. But again, for your own things, depending on the level of risk you can tolerate, we can just replace it with a direct evaluation via Python using exec function, for example. You would be easily able to speed it up 5 to, let's say, 8x. So at the end, this thing will also be super fast. The other nice thing is that it remembers the variable values in the context, and at the same time, it doesn't get inserted in the context of the LLM. And this way, you can really store huge data structures without paying for the LLM to read through all this structure. Instead, the LLM just knows that there is a variable named coworkings, and it can go through all the coworkings in the next run by just referring to them instead of printing this huge data structure that would otherwise take a while to execute. Now let's see how it works. In the repository, we have a simple LangGraph application with just a single node that executes our agent, and inside it connects to the MCP server. The MCP server is stored here. Currently, it aggregates two other MCP servers, one for Notion, the other one is for Google Maps. And it connects to it via STIO, standard input-output, and then composes it and exposes via the server send events protocol. And I will tell you why it's done this way later on. Then we connect to it. We also, this is just an experiment from my end. You can play around with it and finish. Basically, the idea was to also not expose all the tools to the LLM, because it also costs a lot to pass all the information about the tools to the input schema. The idea here was to only select relevant tools for this specific request and then execute only them. And this would also reduce the cost even higher, but this will be for you to explore. You can just check it out here. It's not finished yet. And currently the problem it has, it overfits to the task without thinking further. For example, if I say that it needs to create a database and populate it with the places, it may only select the method of creating the database, the method of searching the places, but it will not think about the distance calculation tool or the tool that creates the items, like this kind of stuff. So it still needs to be worked on, but otherwise you can check it out here. Once we have the tools, we pass them either to create ReAct agent from LangGraph, which is basically this agent pattern that calls actions one by one, or it creates a CodeAct action agent. And for this, we also use a LangGraph library with some improvements I've done. The library itself also works pretty easily. It also exposes a graph inside that calls the model and then executes the code in the sandbox. So it just creates a system prompt that tells the model about the tools that are available and that it has to generate the code. And then it extracts the code snippets from the response. And then if there is a code, it tries to execute the code. And the execution happens using the eval function. The eval function, in our case, is the Pyodide eval function I will be talking about later on, which is basically executing this code in the sandbox in a safe way. And once there is a result, it would again come back to the model call and ask it what's next. In addition to that, I also improved the functionality of this library because it didn't have support for asynchronous tools. As this library's example was pretty basic, it just had mathematical functions, so it was only supporting the synchronous code. But now it also supports asynchronous tools. Also because we use MCPs, for example, the MCP for Notion has dashes in tool names, and this would just not work as a Python code. So what I also did is escaping of these names. And the other big thing I've added is the reflection prompt, because when it generates the code, it doesn't do it well from the first attempt. And I don't want to run this code yet, because otherwise it would hallucinate. And the biggest challenge I was solving with the reflection prompt was avoiding the agent to output the data and instead always referring to variables. The reflection prompt is stored in this file and you can read it through. Basically, this is an extra logic that is not living in the original default prompt, and this way the default prompt stays focused. And that's exactly what happens here. For example, we have Chat OpenAI that basically generates the code. We use GPT 4.1 because it is insanely fast with generating code. But we also use Anthropic because Claude 3.7 Sonnet is really good in generating the good code. That's why we also validate what OpenAI just generated for us. Sometimes the OpenAI code generation model is too lazy. For example, here it just wants to output the first 5 co-working spaces just for demonstration. And then Claude says that no, it shouldn't be just 5, it has to be all of them. So it's really good when you combine these both models. That's basically what the reflection does here. And now you will know why we used SSE as a protocol for the MCP tools. If we go to the evaluation function, we can see that inside it connects to that client. The thing is that we cannot run sub-processes inside the sandbox because it is pretty limited. And the MCP servers we have, specifically for Notion or for Google Maps, are running as sub-processes via SSD.io. And in order to connect to them, the only thing we can do is to do an HTTP call inside our sandbox. So we need to have some kind of a server. And that's basically the thing that the server does. It exposes all the MCP endpoints as a server that we access inside the sandbox. And this way the sandbox is very small. It doesn't have any logic. It just has the functions that have the same name as the tool. And under the hood, it just calls the MCP client and executes that specific tool. You can explore everything in a more detailed way in the repo I will share in the description. The other nice thing is that if you would ask the agent to do something else, it would already have the context about all the variables it had here, and it will be able to access them and do something else. And this is handled thanks to the sessions we have in Pyodide. Basically, we pass the session ID whenever we execute the sandbox. And the session ID is basically the thread ID we have in LangGraph. And this way, whenever you are in the same conversational thread, it would still remember everything which was done before. But there is a limitation. If you will deploy it to a cloud environment, for example, LangGraph Cloud, it will not work well because whenever it will kill the container that runs the application, all the data will be gone. And then it will just not have the access to all the variables. So for you, in order to make it successful, you will need to self-host and you will need to store all the sessions at an external volume that you will need to mount in the Docker container that runs this application. And for this, you can just read the self-host instructions on their website. And the other thing that may also be a limitation for you is working with big lists of data. Although the LLM is prompted to not output the whole list and instead just printing a single item to see the data structure before it plans the next actions on how to integrate with it. Sometimes it may hallucinate and just print everything. So it may also be costly for you. What you can do is to find a custom function that would print not the entire data structure, but instead just the schema of, let's say, the first item in a minimized way. You can name it something like smart print, put it in the context of the Pyodide environment and specify it in the prompt so that it knows that it always has to call this function whenever it needs to output something. And the last thing I wanted to tell you also are the improvements. Currently, if you come back to the latest call, when it adds all the co-working spaces to the database, it does them one by one. It still takes a time, especially if it would be a list of thousands of items. So the thing you can do here is to also prompt the model to optimize these lists in the reflection prompt. so that the main prompt doesn't get overpolluted with the instructions. That will also make it hallucinating more frequently. So here we can say that I want to have batches of, let's say, 20 items every time. You can even do this just as a part of the human message. And in this case, it will be much faster because it will parallelize the things. You can also specify the rate limiting policies from the Notion API, for example, and this way you will be sure that it will not fail and everything will be saved in the database. And one more thing on the tool selection, when it narrows down the list of possible tools to reduce hallucinations. If you want to know more, just let me know in the comments and I will record a separate video, because this is just one of the approaches and there are lots of different ways the AI engineers are solving this problem. This is a huge topic actually, so let me know if you want to know more about this. That's it for today. Now you know how to scale your agent to do thousands of actions while still staying reliable and cheap. Thanks for watching. Don't forget to leave your comments, like this video, share it with your friends, YouTube likes it, and me too. Have fun!